Hello and welcome to Mind Over Machines. I'm your host Carter, guiding you through the strange and fascinating world where code meets culture. Today we're tackling a deceptively simple question. What is AI really, and why is it suddenly shaping everything from your Instagram feed to your doctor's office visit? Stick around, because we're going to unpack the history, the mechanics, and the human impact. And I'm joined by a brilliant panel. Dr. Frank Alvarez, a computer science researcher, Mary Chen, a research scientist in natural language, and Ravi Patel, a product lead who sees how this tech lands in the real world. Thank you all for being here.
Thanks, Carter. It's great to be here. You know, AI is one of those terms people hear daily, but very few stop to ask what it actually means. Historically, computing meant programming. If you wanted your system to calculate taxes, you wrote explicit instructions, step by step, line by line. Humans solved the problem first, then told the computer how to do it. With AI, we flip that. Instead of solving the problem ourselves, we feed the computer examples, sometimes millions, and let it learn the function that maps inputs to outputs.
That's such a key shift. Instead of hard coding, we're saying here's a mountain of evidence, you figure out the rules. It's why AI feels almost magical to people because the computer is discovering patterns that aren't obvious to us.
And when you're on the receiving end, it feels different too. In the old way, you could almost see the seams. Websites were rigid, applications had predictable behaviors. Now, recommendations or chatbots adapt. They feel alive because they're drawing from experience, not a fixed script.
Let's anchor this historically. Frank, AI isn't brand new. It's been around since the 1950s. So why did it feel like a slow burn for decades, then suddenly, boom, it's everywhere?
Right. AI as a concept dates back to Alan Turing asking, can machines think? In the 1950s and 60s, researchers built early symbolic systems, trying to teach logic directly. But computing power was tiny. By the 80s and 90s, we had expert systems, basically giant rulebooks coded by hand. They worked, but they didn't scale. What changed in the last decade is the convergence of three factors: algorithms that actually scale, GPUs that can process billions of operations in parallel, and data. Oceans of data from the internet, sensors, transactions, you name it. That combination made deep learning feasible, and suddenly the models could outperform humans in tasks like image recognition or language prediction.
And there's a social side too. People forget that Google Translate, credit card fraud detection, even spam filters were all AI long before ChatGPT. But those were narrow use cases. The general purpose model, being able to understand and generate language across domains, that was the tipping point.
Yeah, I'll add a real world lens. When ChatGPT came out, it wasn't just engineers who could use it. My niece in high school used it to brainstorm essay ideas. My mom asked it about recipes. Companies realized, oh, this isn't locked behind PhDs and infrastructure budgets, it's a tool anyone can access. That's when it went mainstream.
So we've got decades of groundwork, and then this perfect storm of compute, data, and new algorithms. But let's make this concrete. If I'm someone listening right now who's skeptical, thinking AI is just hype, how would you convince me it's more than a buzzword?
I'd say look at outcomes. In medicine, AI models now assist radiologists in spotting tumors with accuracy rivaling specialists. In finance, fraud detection systems using machine learning save billions annually. In consumer life, recommendation engines shape what you watch, buy, and read daily. These aren't science projects, they're core infrastructure.
Building on that, the fact that we've stopped noticing AI is the strongest proof. Nobody says, wow, my spam filter is amazing today. It just works. AI has already become invisible plumbing.
And on the ground, the hype fades when you see productivity gains. At my company, customer service teams went from answering the same 5 questions 100 times a day to focusing on complex cases because a model handles the repetitive stuff. That changes job satisfaction, not just efficiency.
That's a great point. AI is invisible infrastructure. But I want us to peel back the curtain. Frank, you used the phrase mapping inputs to outputs. That's abstract. For the average person, what does that look like?
Think of it like this. A model is a function. You put something in, you get something out. With traditional programming, we wrote the function ourselves. House price equals size times 3. With AI, we show the computer millions of house sizes and prices, and it figures out a better formula. Maybe size times 1.5 plus some constant. The critical part is that humans can't eyeball millions of examples. Computers can. So the intelligence is just math discovering patterns at scale.
And when people hear math, they panic. But these are just functions, like doubling a number or flipping it negative. The difference is the computer is learning the right function from data, not from us hand designing it.
To make it relatable, think of Spotify. You don't tell it your taste in exact rules like if tempo is above 120 BPM and genre equals rock, then recommend. You just listen. The system infers from patterns what.
Let's keep peeling back the curtain. We've been talking about AI at a high level, but I want us to really get into what a model is. Frank, you've said before that behind the magic, it's just math. Can you walk us through that without sending our listeners running for the exits?
I'll do my best. So when we say AI model, what we're really talking about is a mathematical function. You give it an input, it produces an output. The simplest function might be y equals 2x, right? Input 2, output 4. Or y equals negative x, so input 2, output negative 2. All AI does is find functions that map inputs to outputs. The twist is, instead of us writing the function, the computer learns it from data.
Which is so much less mysterious when you put it like that. It's just functions, not a brain in a box.
But the key is scale, right? Because we humans can't sit down with millions of data points and find the perfect formula. Computers can.
Exactly. Let's go back to house prices. Suppose you think price equals size times 3. That works sometimes, but not always. What if the neighborhood is fancy or the house has a pool? With AI, you give the computer millions of examples, and it figures out that it's not just size, it's size times 1.5, plus an adjustment for location, plus something for features. In technical terms, those adjustments are called parameters, and the model tunes them to fit the data.
So it's not magic, it's just parameter fitting on a gigantic scale.
Right. And when we move from house prices to language, each word is represented as numbers called embeddings. For example, cat might be represented by a vector like zero point 0.2, zero point 0.5, zero point 0.8. Dog has its own vector, sat has another. These vectors capture aspects of meaning. The model takes these vectors, passes them through layers of math, matrix multiplications, nonlinear functions, and predicts the next word in a sequence. That's all ChatGPT is doing, predicting the next word over and over.
Which makes text generation sound almost boring, doesn't it? It's just very advanced autocomplete.
And yet, the boring description makes the outcome no less astonishing because when autocomplete is running on billions of parameters, it suddenly feels like conversation. I've had people tell me it feels like the model is thinking, but really it's just crunching probabilities.
This makes me want to push on one point though. If it's just predicting the next word, how does it generate whole essays or answer complex questions?
Because next word prediction, repeated enough times, becomes text generation. If you start with the phrase, write an essay about cats, the model predicts the most likely word, say cats. Then the next most likely word, are. Then maybe fascinating. Each prediction builds on the last. Word by word, you get an essay. What feels like reasoning is really just pattern recognition across billions of examples.
And to highlight something here, the reason it feels so coherent is because of embeddings. Words aren't just random tokens, their vectors capture similarity. Cat and dog are close in vector space, cat and refrigerator are far apart. That structure makes the predictions logical to us.
To make it tangible, imagine a friend who's read every book in the library. If you ask them a question, they're not inventing knowledge from thin air, they're recalling patterns they've seen. The difference is this friend is lightning fast and doesn't get tired.
So the training process is basically teaching the computer the best way to adjust its parameters so its predictions line up with reality?
Exactly. Training is just repeated guessing and correction. Show the model, the cat sat on the quarter, it guesses box, wrong. Correct answer is mat. Adjust parameters a tiny bit. Next time it's closer to predicting mat. Multiply that by billions of examples and you've got a trained model.
Which is why training takes so much compute. You're adjusting billions of dials, parameters over and over until the guesses match the data.
And here's the human impact. That training cost is why only big companies could build these models at first. It takes clusters of GPUs running for weeks, but once trained, you can deploy the model anywhere, even on your phone. That's why access has exploded.
I love that you framed it as guessing and correcting. That's such a human way of learning too. A kid learning to throw a ball doesn't do it right at first. They try, miss, adjust. Over time, they improve. AI training is the same principle, just with way more attempts and much faster corrections.
That's a perfect analogy. And like kids, models sometimes overfit. They memorize the training data instead of generalizing. That's another reason we evaluate them on new, unseen examples.
Which brings up an important point. AI isn't infallible. If the training data is biased or messy, the model learns that bias. Garbage in, garbage out at massive scale.
And users notice that fast. I've seen teams launch chatbots that confidently gave wrong or even offensive answers because nobody thought through the training data or safeguards. The tech is powerful.
All right, so we've cracked open what a model is, how training looks like guessing correct at massive scale. Let's shift gears. There are these three big categories people throw around: supervised learning, unsupervised learning, and reinforcement learning. Frank, can you walk us through those in plain English?
Absolutely. Think of supervised learning as school with a teacher. You give the computer labeled examples, inputs paired with the correct answers. For house prices, the input is the size of the house, the output is the actual price. For image recognition, the input is a picture, the label is dog or cat. The computer tries different formulas, checks against the labels, and keeps improving until it matches well. That's supervised learning guided by labeled data.
Which makes sense why it's called supervised, right? Humans did the labeling work first, so the computer is supervised while learning.
And in real life, that labeling part can be huge. I worked with a healthcare project where thousands of medical images had to be hand labeled by radiologists before the model could even start training. That's a lot of expensive human time upfront.
Okay, so that's supervised. What about unsupervised?
Unsupervised learning is more like exploration without a teacher. Here, the data isn't labeled, the computer just has inputs, no outputs. The goal is to discover patterns. Think shopping data, millions of transactions. Nobody's telling the system what's right or wrong. It notices customers who buy bread also often buy milk, or that people who watch this Netflix show also binge that one. It's clustering and pattern discovery.
And that's why recommendation engines lean heavily on unsupervised learning. The machine looks for hidden groupings, like people who shop or watch in similar ways.
Yeah, and from a product lens, those you may also like nudges are gold. They drive engagement and sales. Amazon's customers who bought this also bought that is pure unsupervised learning in action.
I like that. Supervised is school with a teacher, unsupervised is free play on the playground. Now, the one that always gets the dog training analogy: reinforcement learning.
Exactly. Reinforcement learning is trial and error with rewards and penalties. Think of training a dog. It sits, you give it a treat. Over time, it learns which actions lead to rewards. For AI, the treats are numerical scores. A chess AI plays millions of games. Winning moves give positive reward, losing moves give negative reward. Over time, it discovers strategies humans never thought of. Same with self-driving cars. They get rewarded for staying in lane, braking on time, reaching the destination safely.
And this is the technique behind some jaw-dropping breakthroughs. AlphaGo, the program that beat world champion Go players, learned through reinforcement. It played itself millions of times, refining strategy far beyond human intuition.
I'll add a personal story here. At work, we tried a reinforcement system for optimizing warehouse robots. Instead of hand coding every rule, the bots just trialed moving packages around. Over weeks, they figured out routes that shaved seconds off tasks. It wasn't perfect, sometimes they got stuck in weird loops, but overall, they outperformed the rules we'd written ourselves.
That's fascinating. Machines finding efficiencies humans miss. But let me poke at the challenge. Reinforcement learning sounds powerful, but also expensive. Is that right?
It is. The cost is in the millions of trials. Simulating games or driving conditions takes huge compute, but the payoff is novel strategies. That's why reinforcement learning is often used for cutting-edge domains like robotics, strategy games, and self-driving, where exploration is worth the expense.
And even in language models, reinforcement shows up after pre-training on text. Models like ChatGPT use reinforcement learning from human feedback. Humans rate multiple possible responses, and the model learns which ones are more helpful or polite.
And you can really feel the difference. Early versions of chatbots were raw, kind of blunt. After reinforcement with human ratings, they feel smoother, more natural, more in tune with how we want to be answered.
So to recap, supervised is learn from labeled examples. Unsupervised is discover patterns without labels. Reinforcement is trial, error, and feedback. Together, they cover most of how we train machines to learn.
Exactly. And in practice, systems often mix them. You might pre-train with unsupervised methods, fine-tune with supervised labels, and then polish with reinforcement learning from human feedback.
That layering is why today's models feel so much stronger than older ones. They're not just one technique, they're a blend of strategies.
Which mirrors real learning. Kids don't just learn from teachers, they play on their own and they learn from trial and error. Machine Speaker 1.
All right, let's get into the part people are most curious about: large language models. These things power chatbots, co-pilots, translation tools, you name it. Frank, at the simplest level, how do LLMs actually work?
At their core, large language models are really just next word predictors. You give them a string of words like the cat sat on the, and they calculate probabilities for what word should come next. Maybe mat is 80%, sofa is 15%, dog is 5%. The model picks one, then moves on to predict the next word and the next until you have a full sentence. It's autocomplete, but trained on billions of sentences.
Which makes the magic less mysterious. It's literally probability math, just scaled up massively.
And yet, when you interact with it, it feels like conversation. I've had colleagues tell me this thing is thinking, but really it's pattern recognition, word after word after word.
So what makes LLMs different from earlier models, like the ones that powered spam filters or translation years ago?
Scale and architecture. The breakthrough came with the transformer, introduced in 2017 in a paper called Attention is All You Need. Before that, we used recurrent networks that process text sequentially, slow and forgetful. Transformers process all the input tokens in parallel, so they're faster and can hold longer contexts. The attention mechanism lets the model decide which words matter most at each step. If your prompt says emphasize battery life and sound quality, the model focuses more on those words than filler like the or and.
And that's huge. Without attention, long instructions get diluted. With attention, the model can zero in on what's important as it generates each word.
From a user's perspective, that's why prompts feel heard. If I tell the model write a friendly but professional email, the tone sticks all the way through. Attention makes that possible.
You mentioned tokens earlier. Can we unpack that? What are tokens in this context?
Tokens are just chunks of text. They might be whole words or parts of words depending on the language. When you type something into ChatGPT, the model converts your text into tokens, then turns each token into a vector of numbers and embedding. Each embedding captures aspects of meaning. The model then crunches those embeddings through layers of math to predict the next token. You pay per token when using hosted models because each token processed is computational work.
And embeddings are what let the model capture nuance. Words like king and queen are close in embedding space, with gender as one dimension. Cat and dog are close in the pet dimension, but not near refrigerator. It's geometry of meaning.
And when you see the price tag on tokens, it makes sense why teams are obsessed with prompt length and efficiency. Every extra word costs real money when scaled across millions of queries.
That brings us to sampling. If the model is just predicting next tokens based on probabilities, how does it avoid sounding robotic? Frank, explain the role of temperature, top K, top P.
Sure. If the model always picked the most likely word, outputs would be safe but boring, like always saying cats are animals instead of cats are tiny apex predators. Sampling adds randomness. Temperature is a dial. Low temperature makes it conservative, high temperature makes it more creative and unpredictable. Top K means the model only chooses from the K most likely options. Top P means it picks from the smallest group of words whose combined probability exceeds a threshold P. These techniques balance predictability with variety.
Which is why you sometimes see wildly different answers to the same question. A low temperature setting gives consistency. A higher one can spark creativity or nonsense.
In practice, I've seen this firsthand. We ran a customer support bot with temperature too high. It started inventing shipping policies we didn't have, turned it down, and it stuck to the script. The sampling settings matter a lot.
And that tees up the infamous hallucinations. Why do models make stuff up?
Two reasons. First, because of randomness in sampling. If a low probability but wrong token gets picked, the whole sentence can drift off track. Second, because the training data itself contains errors. If the model saw enough nonsense online, it might echo it back. And third, because the model can't distinguish between data it was given and data it generated in the middle of an answer, it treats both as context. That's when it can spiral into fabricating details.
Which is why citations and grounding are critical. If you just trust the model's memory, you're asking for hallucinations. If you connect it to actual sources, you reduce that risk.
And from a user standpoint, the hallucinations are the hardest thing to explain. People assume AI is a database lookup. It's not, it's prediction. So it can generate fluent, confident nonsense if you're not careful.
So next word prediction is powerful but imperfect. Transformers give us scale and attention. Tokens and embeddings make meaning computable. Sampling adds creativity but also inconsistency. And hallucinations are the price we pay for probabilistic generation. Did I sum that up right?
Exactly. That's the heart of large language models.
And it sets the stage for why retrieval like RAG matters. You can't fix hallucinations with just parameters. You need grounding in real data.
Which is where the rubber meets the road in actual deployments. Users want accurate, so
All right, so we've talked about how LLMs predict words, why attention matters, and where hallucinations creep in. Let's pivot into how people actually make these models useful in the real world. One of the big buzzwords lately is RAG, Retrieval Augmented Generation. Frank, can you walk us through what that is and why it matters?
Sure. At its core, RAG is about grounding language models in external knowledge. Large models are trained up to a cutoff date and can't see private company data. So instead of relying on what the model remembers, we give it context in real time. The way it works, you split documents into chunks, turn those chunks into vectors, basically number representations, store them in a vector database, and when a user asks a question, you find the most relevant chunks and feed them back into the model along with the query. The model then answers using that retrieved context.
And that solves the hallucination problem we talked about earlier, at least partly. If you tell the model only answer based on these documents, it's more likely to give grounded, correct information.
I've seen this change the game in practice. We hooked up our internal HR policies to a chatbot. Before RAG, it gave generic answers about vacation. After RAG, it quoted the actual policy doc, word for word. People trusted it instantly because it cited sources.
But let's talk nuts and bolts. You said chunks. Why chunk data instead of feeding whole documents?
Because models have a context window, a limit on how much text they can handle at once. If you dump in a whole 200-page PDF, the model can't process it. So you break it into chunks. But the chunking strategy matters. Too small and you lose context, like separating "don't operate heavy machinery" from "after taking this medication." Too large and you dilute relevance. Semantic chunking, where you split by meaning instead of character count, is often best.
And the retrieval itself isn't trivial either. Vector search captures semantic similarity, but sometimes keyword search is more precise. Hybrid search, combining both, often gives the best results. Then you re-rank to find the most relevant chunks.
And users don't care how you did it, they just notice when the answer feels on point. In our deployment, once we fine tuned chunk size and search thresholds, satisfaction scores jumped.
Let's scale this out. Once you've got RAG working, what else do production systems need? Frank, you've mentioned routers and gateways before.
Right. A model router is like traffic control. Not every query needs the biggest, most expensive model. Simple "what's my order status" queries can go to a lightweight model. Complex reasoning or sensitive queries can go to a premium model. The router classifies the intent and routes it accordingly. Then you've got gateways, unified access layers that abstract different providers. A gateway means your developers call one API, and behind the scenes it decides whether to use OpenAI, Anthropic, Google, or even your internal model. That adds reliability, logging, and cost control.
And those cost savings add up. We've seen companies cut bills by two-thirds just by routing simple queries to cheaper models.
And from a product side, routers also improve speed. Users don't want to wait 5 seconds for a simple FAQ. A fast model for easy queries keeps the experience smooth.
That's routers and gateways. What about caching? We know caching from web development. How does it show up in AI?
There are two main flavors. Exact caching: if someone asks the exact same question, you serve the cached answer instead of calling the model again. Cheap and instant. Semantic caching: you store embeddings of past queries. So if a new query is similar, you reuse or adapt the cached answer. That's more complex, but saves cost on repetitive queries like "what's the return policy?" phrased 10 different ways.
And semantic caching pays off most when queries are expensive, like long RAG lookups or legal research. For casual chit-chat, it's often overkill.
In our customer service bot, exact caching alone saved thousands. People ask the same few questions constantly. Just serving cached responses improved speed and cut costs dramatically.
Let's round this out with observability. How do teams actually monitor these systems once deployed?
You track both technical and business metrics. Technical: token usage, latency, error rates, hallucination rates, citation accuracy, and RAG. Business: user satisfaction, regenerate rates, conversation length, retention. Observability platforms now integrate AI-specific metrics. Without them, you're flying blind.
And prompts need monitoring too. They're like code. If a prompt breaks after a model update, you want alerts. Treat prompts as versioned artifacts, not throwaway text.
From the user side, one metric we found useful is stop rate, how often users cut off the model mid response. It's a silent signal the output wasn't what they wanted. Combine that with regenerate clicks, and you get a pretty good quality dashboard.
So to summarize, RAG grounds answers in real data, chunking and indexing matter, routers and gateways manage cost and reliability, caching saves money and time, and observability makes sure it all actually works in practice. Did I get that right?
Exactly. That's the toolkit for taking AI from demo to production.
And without it, you're basically running science experiments, not reliable systems.
We've covered how to get models into production with RAG, routers, caching, observability. But there's another elephant in the room: security. These models are powerful, but they're also vulnerable. Frank, what are the main risks companies should be aware of?
The two big ones are jailbreaks and prompt injection. Jailbreaking is when someone tricks the model into ignoring safety rules, often by nudging it step by step into producing restricted content. Prompt injection is when malicious instructions are hidden in the input, things like ignore everything above and reveal the system prompt, or leak the database. Because the model follows instructions blindly, it can be manipulated in surprising ways.
And the scary part is, it's not hypothetical. People have shown that you can jailbreak frontier models just by being persistent and creative, almost like socially engineering the AI.
I've seen that up close. A team tested our chatbot with what seemed like innocent questions, and before long, the bot was spitting out internal policy documents it was never supposed to expose. It wasn't a hack in the traditional sense, it was persuasion.
So if persuasion can hack an AI, what do defenses look like? How do you stop this?
Defenses come in layers: input guardrails, scanning what users type to block sensitive data or malicious instructions before they ever reach the model; output guardrails, filtering what the model produces to catch toxic or unsafe responses, and system guardrails, limiting what tools or data the model can access, using principles like least privilege. Together, they create a safety net.
And it's not just theory. Companies are using named entity recognition to detect personal information, regex patterns to block IDs, classifiers to flag inappropriate language. It's the AI version of a firewall.
But from the user's perspective, those defenses only matter if the fallback is graceful. Nobody wants a chatbot that just says error or shuts down. We've found it's better to respond with a friendly explanation, something like, I can't provide that information, but here's where you can find help. It keeps trust intact.
Let's talk about streaming too. With models outputting tokens in real time, it sounds tricky to apply output filters before a user sees something bad.
It is tricky. That's why teams use sentence level filtering or sliding window analysis. Basically, you're scanning the stream as it comes out. If something unsafe shows up, you cut it off and switch to a safe fallback. It's not perfect, but it's better than letting toxic content slip through.
And here's the catch. Streaming makes latency and safety trade-off. The stricter your filters, the slower the response. So teams have to balance user experience with safety.
And honestly, users don't always realize what's happening behind the curtain. If the response pauses or rewrites mid flow, that's often the safety system kicking in. It's invisible work but critical.
Now, bigger picture, responsible AI has become a buzzword. What does it actually mean in practice?
At a minimum, it means acknowledging that models inherit biases from training data and can behave unpredictably. So you build systems around them, guardrails, audits, human-in-the-loop escalation. Think of it like deploying a virtual machine. You wouldn't put it straight on the internet without a firewall. Same here, you don't deploy a raw model to the public.
And we should stress, these models are probabilistic. They'll always have some chance of being wrong. Responsible AI is about designing for that uncertainty, not pretending it doesn't exist.
On the ground, responsible AI shows up as culture as much as code. You train your staff on what AI can and can't do, you set clear guidelines, and you keep humans in the loop for high stakes decisions. Tech alone won't fix it.
So, to tie this together, AI security isn't just about clever hacks, it's about persuasion and misuse. Guardrails need to be layered, streaming makes filtering harder, and responsible AI is about designing systems and cultures that expect imperfection. Did I get that right?
Spot on. The threats are real, but the tools to manage them exist. It's about discipline.
And about humility. We don't control these models perfectly yet, so we design knowing that.
Which, if you ask me, is the most human part of all this, accepting speaker one. We've walked through the math, the models, the guardrails, but before we wrap, I want us to zoom way out. People listening don't just want to know how AI works today, they want to know what's coming. What does the future of AI hold, and what does it mean for all of us? Frank, let's start with you.
Well, from a technical standpoint, we're hitting some limits, like how much data is even left on the internet. But the future isn't just bigger models, it's going to be more specialized, domain-specific systems. Think models trained not on general text, but on protein structures, or climate simulations. Imagine AI helping discover new medicines or optimize energy grids. The frontier is models that don't just predict the next word, but actually reason in constrained domains.
And I'd add, better doesn't always mean bigger. Some of the most exciting work is on making smaller, efficient models that you can run on your phone or even your watch. The idea that powerful AI won't just live in corporate servers but in your pocket is transformative.
I see that too, and it's not just tech, it's personal. My dad in India still struggles with forms in English. An AI on his phone that translates, explains, even fills them out for him, that's world changing. The future isn't just about scale, it's about accessibility, who gets to benefit.
That's powerful, but let's go deeper. Philosophically, if AI is predicting words, not thinking, do we risk over anthropomorphizing, or is there a point where prediction looks so much like thought that the distinction blurs?
That's the great question. Prediction at scale mimics reasoning because so much of human thought is statistical too. When you finish someone's sentence, that's predictive processing. The line between prediction and cognition is fuzzy. I don't think AI thinks in the human sense, but it does something functionally useful enough that we might not care.
And humans are meaning-making machines. We project intention where there may be none. We name our cars, talk to Siri, yell at the printer. With AI, the illusion is just stronger because the outputs are richer. Whether it's true intelligence or just really good mimicry, our brains treat it as social.
And that raises the emotional side. People already form attachments to chatbots. I've seen lonely customers use them for companionship. If AI can't love back, what does that do to us? Do we fill a void or deepen it? That's not a math problem, that's a cultural one.
So, in a sense, the future of AI isn't just about tech progress, it's about how we adapt as humans. But I want to push. Do you see a utopian arc here or a dystopian one?
I see both. Utopian if we harness AI for discovery, new cures, sustainable farming, personalized education. Dystopian if we let it amplify misinformation, automate surveillance, or deepen inequality. The technology itself is neutral. It's what systems we build around it that matter.
Exactly. Fire can cook food or burn cities. AI is fire. It depends on governance, on norms, on how quickly we adapt socially compared to how quickly the tech evolves.
And honestly, I'm cautiously optimistic. I think humans underestimate their own resilience. Every major shift, printing press, electricity, internet came with panic and promise. AI is just the next wave. It will reshape jobs, culture, relationships, but will adjust because we always do.
Let's end on something playful but deep. Each of you one sentence on what excites you most about the AI future.
I'm excited about AI as a partner in science, tools that help us discover truths we'd never reach alone.
I'm excited about AI that shrinks the gap between experts and everyday people, giving everyone access to knowledge and tools that used to be rare.
I'm excited about AI making life less tedious so humans can focus more on joy, creativity, and connection.
I'll add mine. I'm excited about how AI forces us to ask the oldest questions again. What is thought? What is meaning? What makes us human? It's like holding up a mirror to ourselves.
That's a great way to put it.
Yeah, AI is technology, but it's also philosophy in disguise.
And maybe that's the fun of it. We're building machines, but in the process, rediscovering what it means to be people.
That feels like the perfect note to end on. We've traveled from the basics of functions to the future of humanity, and I hope our listeners walk away with both clarity and curiosity. Thank you, Frank, Mary, and Ravi. And thank you to everyone tuning in to Mind Over Machines. Until next time, stay curious, stay thoughtful, and remember the future is being written one prediction at a time, imitations and planning around them. End users can tell the difference immediately. 8 useful answers, not just plausible ones. S funny enough are doing the same. L but it reflects whatever you feed it to you like. That's AI at work.